Welcome back, boys and girls. We are on the conductor homepage right here. You'll find the next Youth Maker Home-Based STEM Challenge under Makers. Here's our home-based STEM projects. The recordings we've done so far are attached here on this page. There are some more, and you can get to any of the other ones simply by clicking on any of the links here. It's going to take you to our Flipgrid page. And under there, you'll see that we have actually 8 topics. The most current one that we're going to talk about today is how to make a flat ball. Doesn't that sound like an oxymoron? We don't typically think of balls as being flat. We think of them as being 2-dimensional shapes. But we're going to learn today how scientists use 2-dimensional shapes in computer programming to create 3-dimensional objects in order to help them study the world around us. Let's watch a snippet of an explanation video about how science uses these technologies.
To understand physics, we need to simplify. The world has odd shapes full of rough edges, but in physics, we tend to use round cylinders and perfectly frictionless surfaces. Scientists usually make these simplifications in physics because it is much easier to use math to describe what is happening in a simple situation rather than a complicated one. But could you recreate our real and perfect computer? UCLA professor of applied mathematics, Joseph Turan, does just that.
What really got me excited about math was that you could use the computer with math to make this digital model of the real world that was as realistic as the real world, at least visually.
It uses math and physics to describe how things in our real and imperfect world work. It translates things in our world into mathematical equations that can be solved by a computer.
So these equations, they're basically, they would tell you everything about what's going on if you could solve them. But they're so complicated that we can't solve them as is. We have to only approximate them. That is the branch of math called scientific computing and numerical analysis, where we use the computer to get a very, very accurate estimate to the solution to the physical equations.
Joseph's work has very important applications, from Hollywood movies to the medical field.
Basically, you use the computer model of the real world to try things out that would cost you a lot of money to do in real life. If you want to have a movie effect of like a dam break, basically, if you want to get the dynamics of the fluid as it breaks the dam just right, if you want to get it so that it looks like a real dam break, or the effect looks right, you have to have the mathematics and the physics right behind it. So you have to bring someone in that's outside of just the artistic world, because if you just try to sort of draw a dam breaking, it's going to be really hard to get it to where it looks like it really was the physical phenomena happening.
It's creating a type of computer program that creates a 3D copy of a surgery patient. Not just any person, but an exact copy of the person having surgery. So the doctor can practice on the 3D version first.
If you're doing open heart surgery and you make an incision to the patient, you need to have the response to the incision be the same in the video game as it would be in real life. You would want the tissues to deform in a way that was different than they would be when you went to do it to the real patient.
He expects that the hardest objects to simulate are those that are elastic. Objects that are squishy and change shapes, but don't break very often. Try to press on an area of your arm, for example. You will notice that it bounces back to the original shape. This is because it has elasticity.
Spring is the easiest to describe elastic object. You just have 2 point masses at the ends of the spring, and they just bounce. So as they compress, you'll have forces that repel the 2 points in the spring, and as they extend too far, the spring will want to pull them back together. So you'll have basically these forces that are either pulling them together or pushing them apart. And you can think of the object as being made up of a whole bunch of different springs.
Joseph uses simple physics, uses laws of motion, to understand how complex shapes of materials deform when you push or cut them.
Most of the ideas don't work. So we usually say, let's try this different discretization of the problem.
Okay, as you can see, math isn't all that bad. It started as playing. People were observing things in the world like the slinky, a spring, the rubber band, things like that, and that's what we're going to try today. Your challenge is to use two-dimensional shapes to create three-dimensional objects. Okay, and here is a picture of a soccer ball to get us thinking about how this actually works in our world. So as you can see, the solid black shape has 5 sides, 1, 2, 3, 4, 5. And the white shape has 1, 2, 3, 4, 5, 6. So we have pentagons and hexagons. And when we combine them by their edges, it's going to take those flat shapes and create a three-dimensional sphere. So that is going to be your challenge today. Let's look at the demonstration here for you. So you're going to need very simple supplies that you probably have laying around your house. You're going to make a template as symmetrical as possible. We know that any 6-sided shape is a hexagon, but there are things called regular hexagon where every side of the hexagon is the exact same length. That's what you're trying to accomplish in this build, in this challenge. And use combinations of shapes. Like you saw, they had hexagons and pentagons. Okay, so that's your challenge today. Build a sphere, which has no straight lines. You're going to use straight lines and flat shapes to do that, such as squares, triangles, pentagons, hexagons, or any other shape that you can think of. I can't wait to see what you guys create.